Welcome to the annual Wiley Prize in Biomedical Sciences. I'm Deborah Wiley, and I head the Wiley Foundation. Every year we host this at Rockefeller University, and this year it is a pleasure to have Rick Lipton here as the new president of Rockefeller University. And for those of you who might or might not remember, Rick received the Wiley Prize in Biomedical Sciences in 2008. This year's prize will be the 16th one that we award by our distinguished jury, some of whom are present today: Günter Blobel, Kai Salicati, Wayne Hendrickson, and then Tizia DeLong, Robert Horvitz, and Joan Stites. Joan today is being represented by her husband, Tom. Wiley continues to enjoy a productive and successful partnership with the scientific community for the advancement of research that began over 210 years ago. The Wiley Prize in Biomedical Sciences was conceived as a way to give back to this community. We chose to focus on biomedicine because of the extraordinary progress and change that continues to take place in that field. Our goal is to recognize specific contributions that demonstrate the nominees' significant leadership in the development of research concepts or their clinical application. Particular emphasis is placed on research that champions novel approaches and challenges accepted thinking in the biomedical sciences. We are pleased that previous winners of the Wiley Prize have gone on to win the Nobel Prize in Physiology or Medicine, including last year's winner, Yoshinori Oshumi, Robert Horwitz, who, as I mentioned before, is a jury member, Andrew Fire and Craig Mello, Elizabeth Blackburn, and Carol Greider. We're also pleased that 12 Wiley Prize winners have received the Lasker Prize in Basic Medical Research over the years. The Wiley Prize in Biomedical Sciences is being awarded to Joachim Frank of Columbia University, Marin van Heel of Imperial College London, Richard Henderson of Cambridge University for their pioneering developments in cryo-electron microscopy. As one of our board members, Joan Stites, commented, "You can't open a journal today without reading about research results and advances that are obtained using this technique." So, we are now going to make this award and then continue on. So I'd like to invite Joachim, Marin, and Richard to join Günter and Wayne Hendrickson up here, and we will make this award, and then Günter and Wayne will take over from there. Thank you very much.
So I will not give a long speech. I'm the chairman of the jury for the Wiley Prize, and we are very happy about our selection for this year's prize winners. And we are very glad that you turned out in such large numbers for the lecture. And I give the baton now to Wayne Hendrickson, who's part of the jury as well, to introduce the speakers, and one after the other, they will then deliver their talk. Wayne.
Correct. That's our plan.
So you can sit down again.
Okay, before we hear from our Wiley Prize winners this afternoon, let me just say a few words about the selection that the Wiley Foundation jury has made, why now, and why these recipients. As you have heard, we are recognizing Frank, Henderson, and van Heel for their contributions to the development of electron microscopy in the structural studies of biological molecules and complexes. This is an exciting time for structural biology, and particularly so for cryogenic electron microscopy, or as we call it for short, cryo-EM. What has been called a resolution revolution is taking place. Atomic level structures from cryo-EM images now rival those that have standardly come from the technique of X-ray crystallography, and exciting structures that had previously eluded analysis are being published with astonishing frequency and in remarkable detail. Recent technical developments have been instrumental for these breakthroughs. Notably, there have been transformative advances in detectors, in specimen preparation techniques, and in computer programs for the analysis of the data. However, it was because basic procedures were developed well in advance of that these techniques could take off with such astonishing quickness. The fundamental methodologies, concepts, and experience in single particle reconstruction that had their origins in pioneering work from many years ago are responsible for this, and it's that we recognize today. I won't say more about that because we will be hearing in detail, I think, from our recipients, and I'll let it be at that. But let me introduce these people, who I'll do one at a time, and we'll do this in a very nice order. It happens to be alphabetical, but I believe it also is a good order. So first of all, let me say something about Joachim. Joachim Frank's early training was in physics, and the doctoral research is carried out at the Max Planck Institute for Biochemistry in Martinsried and at the Technical University of Munich. His postdoctoral research was somewhat peripatetic and included stops in Berkeley, where he worked with Bob Glaser, who was one of the key figures in bringing the cryo into cryo-EM, and with Richard Henderson in Cambridge, who we'll hear from later. Joachim moved to the Wadsworth Center in Albany in 1975, and he came to Columbia in 2008, where he is an HHMI investigator and a professor of biochemistry and molecular biophysics. He is a member of the U.S. National Academy of Sciences and of the American Academy of Arts and Sciences. His previous honors include the Franklin Medal from the Franklin Institute in Philadelphia. Joachim, your floor.
Thank you very much. It is a great honor to stand here and be recognized in this way, along with the distinguished prize winners in the past. Okay, so to begin with, I would like to thank the jury of the Wiley Foundation and all the past and present members of my group since 1975. The collaborators around the world, and a big thanks to my wife, Carol Sassanov, for her support over many years. She's here today. Thank you. So to begin with, I found it necessary to give some introductory material for people who are not as familiar as maybe this audience. Molecules and life. All life processes are constituted by interactions between molecules in the cell. And molecules have intricate structures, and they're defined by their atomic composition and arrangement of these atoms. If you want to understand the processes on the most elementary level, we need to know these structures and how they change as the molecules interact with one another. And in fact, medicine over the past few decades has been greatly transformed because of the knowledge on molecular structure accumulated during the past 50 years, and in the process has in fact become molecular medicine. So these are just some of the examples of molecules in the cell that are behind very fundamental processes. And X-ray crystallography, crystals, in crystals, many copies of a molecule are arranged in very regular order. An exposure to the X-ray beam, we obtain diffraction patterns, and from there we can determine the structure. And I show here Max Perutz and John Kendrew with a model of hemoglobin obtained in 1982. The X-ray beam must be high intensity, crystals must be almost perfect. And today, 100,000 structures solved by X-ray crystallography are available in public databases. But crystal packing means that molecules are not visualized in all conformational states that are important for function. And many molecules don't form highly ordered crystals. And sample quantity can also be an issue. Sometimes very large quantities are necessary in order to grow crystals. So electron microscopy can also be used to solve structures. Projection images are formed with very high magnification, so for instance 30,000 times or even larger. But to reconstruct an object, many different views must be collected. And this sample must be thin, very thin. Electrons are readily absorbed by matter. And electrons strongly damage the molecules. There is a need for low dose. 10 to 20 electrons per square angstrom are now sort of the norm. And low dose means that the images are very, very noisy. And from there follows the need for averaging. So in the beginning, electron microscopy was used for high-resolution structure research, and they were used by making use of implicit averaging and tilting. Either two-dimensional crystals, such as Richard Henderson and Nigel Unwin worked on in 1975, or molecules with high symmetry. This goes back to the groundbreaking work by de Rozier and Klug on the bacteriophage tail that was published in Nature 1968. That was the first 3D reconstruction. So single particle techniques in contradistinction has an entirely different concept. The structural information is obtained from images of single molecules. Single doesn't mean one molecule only, but they are single in the sense of a single spar, unattached. And they have to be available in many copies. And molecules are free to assume all naturally occurring conformations. Molecules are randomly oriented. And so a single snapshot may already give us hundreds of particle views and enough information to get started with the three-dimensional reconstruction. And as we collect more and more snapshots, more and more orientations will be covered until we have enough for reconstructing the molecule in 3 dimensions. So this realization, although not with any kind of certainty, I published in 1975. I realized that this would be a way to go. And I'm reading from the abstract here: the investigation concerns the possibility of extending the non-periodic objects, the low exposure averaging techniques recently proposed for non-destructive electron microscopy of periodical biological objects. And the reference is specifically to Unwin and Henderson, because that was the talk of the town. Everybody was very excited about this. And so the challenge was to extend these techniques to single molecules. But the talk was very cheap. The work was actually very hard. And the projection images of the molecule need to be aligned with one another. is one thing. The concept and measurement of resolution had to be defined in the absence of diffraction patterns. And diffraction patterns make it easy to state the resolution. And to do a reconstruction, one needs to know the angle of each projection. And the angles have to be determined without knowing the structure to start with. And how to deal with heterogeneity. It's a very big point. How to develop programs as new ideas come along. How to avoid rewriting a program each time you change your mind about the approach. So to go to the last point, the idea that I had was to first make myself a workbench, a modular program with many programs that sort of could be used in an interchanged way. And so today, when you look in Wikipedia and look for image processing programs in electron microscopy, you see a very long list. This is even only a partial list for the general packages. And one of them is the SPIDER package, and that was developed in 1981, and in fact an abstract was there in 1978. So without it, the work would have taken years and years. So there were two basic things that I knew from my PhD thesis in 1970. EM images can be aligned within 1 angstrom. And you see here a cross-correlation peak. Oops, that doesn't work. A cross-correlation peak in the cross-correlation function that shows the precise relative alignment of 2 images. So it's doable, and I had a certain amount of confidence from that. Another one is the resolution. The concept of resolution, if we have aperiodic specimens, resolution can be defined as the extent of reproducibility in Fourier space of 2 independently collected signals. And so this is here. This was done here by the so-called method of Young's fringes, in which 2 images are simply put together on an optical bench and then shifted against each other. And then you see this fringe system, and the extent of that fringe system tells you how far the reproducible resolution goes in Fourier space. And that really spawned a lot of measures that were introduced later on. So alignment and averaging, using these kind of tools, a proof of concept was published in 1981, 40S subunits of HeLa ribosomes. And you see the tremendous increase in signal-to-noise ratio in this in the average at the lower left. So, but the very big problem was the problem of heterogeneity. Molecules are not only in different orientations, but they are also in different conformations and binding states. And this is shown in negatively stained micrographs here, the so-called LNR, left and right views of HeLa ribosomes, which were shown in the previous slide, and then the flip and flop views of hemocyanin. So there came a very fortuitous and very productive time of work together with Marin van Heel, who visited for a few weeks as a student. And at that time, we, in some great brainstorm, came out with using multivariate analysis of aligned molecular images. And they really radically solved lots of problems right at the beginning. And you can see that the hemocyanin is something like an ideal test specimen because it comes in these very peculiar attachment states and oligomeric states, and which look different in flip and flop view and also have some rocking behavior. And there was an element of serendipity. The multivariate analysis existed there in laboratory medicine at the Wadsworth Center And so we met Jean-Pierre Bretaudier, who was one of the scientists doing laboratory medicine, and he got all these printouts, and then we got this realization that patients, if we think of patients as images or images as patients, and we think of the pixels as blood sample measurements, then we have solved our problem. And in fact, we plugged the programs together, and all of a sudden it worked. So there was an element of serendipity right at the start. Now, one of the most important development in cryo-EM is, of course, the switch over to frozen hydrated specimen, freeze plunging, vitreous ice, cryo-EM. So the molecules are embedded in vitreous ice, and so they're not affected by air drying, and they can happily be in a state which is the native state as they encounter in water. And the pioneers were Bob Glaser, who, as you heard, was my mentor for a short time, for a short period of several months in Berkeley. And then Jacques Dubochet, in 1981, made the technique really work. And then the other thing that needed to be solved and was then approached in different ways was how do you find orientations. Now, my group came up with the random conical reconstruction method, which is very difficult to explain in a few moments, and it suffices that the concept was formulated for an overhead. Nobody knows nowadays what an overhead is, but that was one of the last things that I found. So in 1978, the concept, and then it was realized with computer programs by Michael Radermacher, and we got the first 3D reconstruction. So there is a way, and there are now several ways, to get the orientations of molecules without knowing the structure to start with. And this is really one of the core elements of many approaches nowadays. And once you have a beginning structure, then you can do iterative angular refinement, essentially going around the loop, and first produce a library of projections from the starting structure, compare this library of projections with each experimental projection, and get more and more refined angles. And you go around and around. And this kind of engine is really behind all the current approaches in single particle cryo-EM. And it's very difficult to go through all the different milestones and elaborate on these. There have been so many years in between. I just wanted to highlight the very beginning of these. And you see in the foreground a ribosome at 2.5 angstrom resolution, which I would never have thought would be possible. So I'll go with a few other examples in between. I just want to particularly highlight the early work in calcium release channel in 1989 and 1994, because we just recently published a paper of a structure at 3.6 angstrom resolution, and that highlights the incredible progress that we have obtained. And this was another milestone, E. coli ribosome for the first time seen in very great detail. One sees the tunnel and the interface canyon and the mRNA channel. And obviously, here being at Rockefeller, I have to show you this as one of the first in the collaboration with Günter Blobel, the first visualization of the translocon. So this was a great amount of excitement. And Roland Beckmann was the postdoc at the time, and obviously you know about his flourishing work now in Munich. And then there were the first evidence of conformational changes during the work cycle, plus minus elongation factor G. We see a very dramatic change in the conformation of the ribosome, indicated by a ratchet-like motion. So this was a very big milestone. And then, going all the way over to 2013, the best resolution from recording on film was 5.5 angstrom. And we managed to get an atomic structure out of this by flexible fitting and so forth. But then, of course, here's the slide that all three of us are going to present. The new cameras came along, and they produced an incredible change in this entire industry and brought us where we are now. And I show you one of the results that we have obtained. It was one of the first that we obtained with a new camera, which also shows that we get several structures from the same sample, and I like to call it a story in a sample. So we get an entire story out of a sample, and of course we need to connect the dots in some way. So this is an example for the use of the maximum likelihood 3D classification method that now everybody uses, and that originated with Sears. This is a T-cruci ribosome large subunit at 2.5 angstrom resolution that I showed you before. And incredible, I found myself looking at the water molecule. Water molecule by single particle cryo-EM. I could not believe it that we get to this point. And of course, we see magnesium atoms, and we see all the signatures of amino acids. This is another work that I'd like to highlight. The AMPA receptor at TWOMI is here in the audience, managed to get a paper into Science after being with us, with Sasha Sobolewski and my group, for only 2 years. And then finally, ryanodine receptor, you see the comparison between the 45 angstrom and the 3.6 angstrom structure. Now we're really in business. We can really look how the channel works. And we got a little bit beyond this now, because there are methods that make use of the entire ensemble. By exploring the entire ensemble of molecules, in this case we had 400,000, and could look at these with a new technique which is called manifold embedding. And we see the energy landscape and can actually sort of draw a trace that the molecules very likely go through in order to go from the closed to the open state. And I'm showing you, let's see, I don't have nothing to operate with this with. Okay. All right. Okay, so now you can see a series of structures. These are actually 50 structures along this pathway. They are not obtained by morphing between one structure and another structure, but rather these are actually structures reconstructed at all these different points of the energy landscape. And let's see. We have another view of the channel right there. So you can see this intricate connected movement of all the different helices. So, in conclusion, single particle cryo-EM, a new era in structural biology, a bright future. There is no need for crystals anymore. Very small sample quantity is needed. resolution in the 3 to 4 angstrom range can now routinely be achieved. Multiple structures can be retrieved from the same sample. Molecules are in close to native conditions. And solving structures of membrane proteins is much easier now than with X-ray crystallography. And the analysis of large ensemble manifold embedding yields the analytic landscape. One thing that it didn't talk about is time-resolved cryo-EM because of the shortness of time, but this is another very promising development. And this is sort of the modest growth, but you see an exponential trend in the number of EM structures, EM maps and EM structures deposited in the PDB. This is going to really skyrocket. And I managed to find a picture of sort of the 90s somewhere, and the Gordon Conference is always a place where the alumni come together, and so this is one of those pictures where some of the very important people are sort of grouped together. And this is the current picture taken in the last July. In July, we always go up on the roof of the Black Building. Thank you very much.
Thank you. I don't think we warned everybody, but we're going to hold the questions until the very end. So remember what you, please try to remember. Okay, so the next speaker will be Richard Henderson. Richard was trained at the University of Edinburgh in physics and then moved into biology at the MRC Laboratory of Molecular Biology in Cambridge. His dissertation project with David Blow produced the X-ray crystal structure of chymotrypsin, one of the very first crystal structures of proteins. He went on to a postdoctoral fellowship at Yale and then returned to the LMB in Cambridge, and he stayed there, including as a stint directing the laboratory himself. He's a fellow of the Royal Society and a foreign member of the U.S. National Academy of Sciences. His most recent award prior to the recognition of the Wiley Prize, Wiley Award here, was the Alexander Hollander Award from the National Academy of Sciences. Richard.
Thank you very much, Graham. Thank you. Right, well, it's a really great pleasure to be here, and it's particularly nice when scientists who you've admired yourself are on the committee that seems to think that what we've been doing is worth acknowledging as well. So many thanks to the Wiley jury. So obviously all of us have come via different trajectories to end up doing single particle cryo-EM. So I thought it would be most interesting for people here to know a little bit about my own trajectory. So I've put this title From Electron Crystallography to Single Particle EM and tell you a bit about this sort of path that I've followed from one thing to another, each time trying to be following the line of most productivity and least resistance. So when I started out as a student in Cambridge, I went into an office, and the guy sitting next to me is called Peter Brecher, and he was working on crystals of myoglobin with John Kendrew. And my project was to work on crystals of chymotrypsin. And actually, soon after I started, Tom Stites joined the group. And this is from our joint work on some of the chymotrypsin substrate and ligand binding work that we did in 1968 or 1969. So it's really great to see Tom after so many years. And then after doing X-ray crystallography, I switched to being interested in membrane proteins and went to Yale, where very soon Tom showed up as a young assistant professor. So again, I had a contact with Tom. And after trying various other things, decided that it was a good project to work on this halobacterium bacteria that had these 2D crystals of purple membrane, bacteria rhodopsin, that Walter Stekenius had discovered actually while he was here at Rockefeller before he went to UCSF. And what we did was to, as they had done before, actually isolate these 2D crystals, which is maybe 100 molecules in each direction, so that would have 10 or 20,000 unit cells, but it was only 1 molecule thick. But you could isolate them, and this is how they looked like on an electron microscope grid. This is the very thin film of carbon. These are the crystals. Each one is a single crystal, although some of them might have a sort of little parasite on the side, and their electron diffraction pattern looked just like the patterns that we got with X-ray crystallography, except it's a 2D crystal instead of a 3D crystal. And then with Nigel Unwin, and I think Joachim already mentioned this, we went on initially at room temperature and got this model in 1975 at about 7 angstrom resolution, showing 7 transmembrane helices. And then we were kind of stuck because we were at room temperature, and we tried all sorts of other things until about 1983 or 84. Wachu went to Berlin and showed that you could get really good high-resolution pictures, 3.9 angstroms of chrotoxin. So we switched to doing not only electron diffraction, but electron imaging in the cryo-EM. And then we were able to go from, that's the same map I showed you, 1975, gradually over about 15 years to finally get a map at about 3.5 angstroms in which all the data was cryo-electron diffraction and cryo-electron imaging. And we're able to fit in the sequence of bacteriodopsin that was known by then and build an atomic model in 1990. And then a little bit into the early 80s, as Joachim mentioned, Jacques Dubochet had been hired by John Kendrew as a group leader at the MBL to figure out the behavior of water so that you could then do frozen specimens in the EM. And we sent one of our students from Cambridge, because so we knew about Jacques' work, 1982, 84, and this particular review is in 1988, showing 2 of his early plunge freeze apparatus, where you have the EM grid here, you put the little drop of buffer solution containing viruses or ribosomes, bacteria, and so on, blot it, and then plunge freeze it into ethane, liquid nitrogen temperature. They have a gravity-fed one and an elastic band one. And we sent our student to the very first cryo-EM course, and when he came back, he wouldn't work on our project. He says, cryo-EM and plunge freezing, this is the future. So we lost Guy Vigers, who was a student with Linda Abos and I, to Tony Crowther and Barbara Pierce, and he worked on clathrin, and that was one of the earlier structures. And then another thing that happened is I was asked by Carl Brandane, who was at that stage the director of the biological sciences at ESRR, the synchrotron, and they were having a meeting to decide whether to put money in, 10 million euros or something like that, into an X-ray microscope. And those of us who sort of knew about this, we knew that X-rays, although they were wonderful for big crystals, were 1,000 times worse in terms of the amount of radiation damage they created per useful elastically diffracted event, which is the thing that gives you the high resolution. So I went along to this meeting, and there were about 50 X-ray microscopists, and they didn't know this. So I almost got lynched at this point. So I decided that, if these people who are highly intelligent scientists didn't know, better write a review. So I ended up writing this review, which the main goal was to point out how good electrons were. And initially it was just a comparison of electrons and X-rays, but it turned out neutrons, even though you think they do no damage, there are nuclear reactions that convert, let's say, a proton into a deuteron with recoil energy, and they do 3 times more damage than electrons. And so having done this, I thought, well, maybe we should figure out how many images we might need to get a high-resolution structure by electron microscopy. And apologies to those of you who are experts who've seen this slide before, but this is our table, and you don't need to look at it. But the idea was to calculate from first principles, not bothering about whether anything worked or whether detectors worked and so on, but just assuming everything was absolutely perfect. How would it work for a large virus or a small virus down through a ribosome, right down to tiny little proteins like cytochrome C or lysozyme, and then to work out, if you got a really good image, could you see the particles in a thin film of ice by the Dubochet method? And the answer was in this column that anything above 5 or 6 kilodaltons you could see. Below that, you'd have a hard time because there'd be noise fluctuations just from the electron dose. And then above about 35 or 40 kilodaltons, you ought to be able to find the orientation. It wasn't a very accurate theory, didn't include an envelope function, but it was a guide. And then the final column was the number of molecules you'd need to get a 3D structure. And we were very conservative. This was a criterion that you should find the Fourier components at 3 times the noise level, so a 3 sigma criterion. And the reason the number is the same for all of these different structures is that for the big structures, like a big virus, adenovirus, you need a lot more views using this pi big D over little d, diameter and the resolution. The number of views you need that David de Rosy and Aaron Klug had worked out, you need more of them for the high resolution, but for the small structures where the contrast and so on is low, you need to average more identical views to get the signal to be at this 3 sigma level. And then when you work it out, it cancels out exactly. So that was our idea. So,
I just want to swap her clip out. It's very noisy.
Too near me, is it?
Yeah, a little bit, yeah.
All right. So then not everybody believed this. So we took recently some images that give you an intuitive feel for it. And so this is a picture of a 1.5 megadalton pyruvate dehydrogenase icosahedral enzyme complex, where you can see 5 folds, 2 folds, and 3 folds. And then as you go down in size, this was beta-galactosidase, 0.5 megadalton. This is a pentraxin that Mark Pepys in London had worked on. It's 5 identical 25 kilodalton subunits with a ring of 5. So you get the top views, and then you get the side views with these little lines and little circles. And if you go smaller, down to, this is 40 kilodaltons, then you see more or less little, a little bit of shape, but little black dots. And obviously you go smaller, you get smaller and smaller dots until they sort of disappear into the noise level. So we were kind of happy with that overview. And then continued. So then we switched, based on this analysis, we switched our interest from being electron crystallographers round about 1995. So unlike Marin and Joachim, we were only relatively newcomers to single-particle EM starting about 1995. And then we stopped our crystallography because we tried to make crystals, and it turned out to be just as difficult to make 2D crystals of membrane proteins as it was to make 3D crystals, although quite a few structures were solved, not as many as we'd hoped. So we switched to the single particle area, and we thought with Peter Rosenthal it would be a useful thing to have a kind of theoretical overview, a kind of framework for thinking about this. And so this is from a paper in 2003 with Peter Rosenthal. And the idea here is, what is the average structure factor of your single particles in ice that you're trying to determine the structure of versus the resolution? And in X-ray crystallography, there's something called Wilson statistics, which says once you're at reasonably high resolution, the average structure factor is the square root of the number of atoms. So that black line is the square root of the number of atoms, and then there's a form factor, so it fades a little bit more than that, so there's a slight fading with resolution because the atoms have a certain size. And then at low resolution, the atoms are all scattering in phase. So if you've got, let's say, 100 angstrom diameter biological structure, and you look at 200 angstroms, then all the atoms are scattering in phase. So this is a solvent-corrected 0.28 times the number of atoms. This is the number of atoms. This is the square root of the number of atoms. And then the noise level, when you work it out according to that theory, if you only have one view or you fractionate it to have all the views and get a 3D model, but just from one structure, the noise level is quite high. And you can't ever, that was the same as that previous slide, you can't determine the structure from one image. There's too much radiation damage and it's destroyed. But you can ask whether you can find it. And if you follow that line across, it does intersect. And you can find the structure at maybe 20 angstrom resolution without any averaging because of the envelope function. And then this region from low resolution to 10 angstroms, it varies depending on the solvent contrast. Has it got holes in it? We call this the shape solvent region. And it was known, if you change the density of the solvent in a 3D crystal by X-ray crystallography, the spots beyond 10 angstrom don't change much when you change the solvent. So once you get clear of that solvent region, you're into this Wilson statistics region. So the goal of the single particle, as we were sort of formulating it, was to average enough images so that the noise would go down here. That would be 10 images, 100, 1,000. You're bringing the noise level down, but the average structure factor from the things you're imaging is staying the same. And once the noise level gets below the signal, you've determined the structure of all the Fourier components, and therefore the whole structure. And the idea was it was 10 or 12,000 in those days, although Peter said we were being, and I'll show another slide in a moment, we're being a bit too conservative. The X-ray crystallographers never did determining their Fourier components at 3 sigma. It was all about 1 sigma or 0.6 sigma. So 60-degree phase error, figure of merit of a half. So we put around about 1,000 here. But in reality, these images that we work with, and that's still true today, even with the new detectors, the new microscopes, the images are not perfect. So there's an extra blurring factor that is in the image and in the microscope. So instead of it being according to beautiful theory, it fades a bit faster than that. This is the image blurring factor, B factor, temperature factor. And it comes down, and when that curve showing the average intensity reaches the noise level from whatever number you've averaged, that determines the resolution you're at. And then you go beyond that, it's mostly noise. Below that, it's mostly signal. And then, of course, in the computer, you don't determine the orientations of the particles terribly accurately. So there's an extra computational B factor, which makes it go down further. And in the structure that we were working on as our test specimen in 2003, we picked this pyruvate dehydrogenase icosahedral, and with 3,500 particles, each with 60 copies, which was 200,000 asymmetric units, we reached 8.7 angstroms. And this is entirely experimental now. This is the curve in the low-resolution region, the solvent region. Then we get to the region where it follows a B factor, and then you get to the noise level here. And we had these formulae that can correct the signal for the noise level, and that thin red line is the extracted value of the signal as it comes down. And when it reached about this region, the noise and the signal were equal, and that was the resolution. And then what Peter did was to rescale this, and the B factor was 1,000. And in X-ray crystallography, people like it if it's 30 or 40, and at the outside, 100. But this is a very, very strong fading, and that's why it's not a very high resolution. And so the goal was to get better images, get computer programs, so that you could bring that B factor down and get this curve up here, so that with reasonable numbers of images, you could still determine the structure. So if we jump now to some structures taken with the new microscopes and the new computer programs, this is 3 of them, and this is a different way of working out the B factor of the data. So I'll take this one on the bottom first. This is from Radostin-Danev's group with Baumeister in Martinsried, and they've collected a really big data set on the proteasome, and this is the resolution squared, and this is the number of particles that they've put into their procedure, and then you just run it with different numbers of particles, and the more particles you have, the higher resolution you get to. And the fact that this line is relatively straight as a plot of the log of the number of particles versus the resolution squared, that's essentially the same as the plot I was showing you from Peter Rosenthal's work, but it is much more objective and reliable because it doesn't depend on you knowing the MTF of your detector, anything else. It emerges from the quality of the data and the quality of the computer program. So this is the overall B factor for everything. And you can see a lot of them are 100, 100, 88, and there was 84 and so on. And they're mostly roughly a straight line. There may be a hint of it, some other effect of coming in here. So the conclusion is that these type of plots are very useful. Plot of the number of particles versus resolution. If it's linear, that means there's really a single blurring factor that's describing the fading. And then you can have, if you want, let's say you've determined a structure like here at 3 angstrom resolution, and you want it at 2 angstrom, you can figure out how many more particles you need to reach that. And then you have to decide whether you're willing to put that work in, or whether maybe you'll go on holiday for a bit until the equipment gets a bit better, and then you can come back and do it again. So and then if you take the second 2 paragraphs, these are quite big numbers. But if you look at 4 angstrom resolution rather than 3 or 2, the number is 5 or 10,000 only. And if you say 6 angstroms, it's about 1,500, or 10 angstroms, which is where this solvent region of the predicted structure factor is beginning to fade out, it is about 800 or so. So we think it's this data gives you a second reassurance that we're thinking of things and we haven't done the calculation wrongly. So then I thought it'd be interesting, and Joachim already showed this slide. These are various people's efforts to look at the theoretical minimum number of asymmetric units you need and the size of the particle you need to find the orientation. And then on the right is how the experiments have evolved. And this is the same paper that Joachim showed in 1975. There's a lot of discussion about it. Estimates didn't come in until a bit later. And this was the bit of the review that I showed you with 12,000 that we revised to 600. And in between, Bob Glaser also said this was too conservative and came out with a number with a different model of about 1,400. By comparison, the experimental number of data people were using in our 2D crystal case, or Werner-Kuhlbrandt's light harvesting complex, we were using millions of particles. And the early single particle were also using millions of particles. Yet we were saying you only need 1,000 or something like that. So then the new detectors came in around about 2012, 2013, and suddenly the images were better, the orientations were better, and this worked synergistically together. And so nowadays people are using 30 to 100,000 particles. So we think that there's still, this is our latest guess, we still think that there might be, having got a 50-fold improvement from the interaction of the new detectors with all of the other algorithms, we still think there's another quite big factor coming that will make it much easier to determine. So then I've got a couple more things. This is the same slide that Joachim mentioned. This was the film that we were using at 300 kV. This is the, roughly speaking, doubling of the detective quantum efficiency. That's the proportion of electrons you detect that you get with the new detectors. And one thing that a lot of people are doing with the K2 Summit, which does electron counting, is you turn the magnification up so that instead of this being 2 angstroms, it might just be 1 angstrom. So then 2 angstroms is here, and then all the data out to 4 angstroms is recorded with a higher DQE. So the goal for the future then is to get all of these up to 100%, maybe with a little bit of fading. And that will be happening, although not absolutely immediately. So then, using these detectors, I'm just going to show one structure that in 1996 or so, when we said single particles is the future, we thought we should be working not on helical or icosahedral or 2D crystals, which the lab in Cambridge had focused on in the years before that. And also we said there were a lot of people working on ribosomes, so we wanted a single particle without symmetry that was not a ribosome. And this is mitochondrial complex 1 that John Walker's group had been working on. And Vinoth recently, but I'll go back in a moment, about 2 years ago and so on, Judy Hurst came across from the MRC mitochondrial biology unit with a sample of this mitochondrial complex 1, which is 45 subunits, 900 kilodaltons, and said, we've been trying to crystallize this for 10 years. We've got crystals, they don't diffract very well. Why don't you have a little look at the sample? So Vinoth, within a month or two, had this map with the 8 iron-sulfur clusters. If you contour it at high level, you can see them here. NAD each puts the electrons in. They flow down into ubiquinon in the membrane. The membrane domain has 76 transmembrane helices that you can see. If you go down to a lower contour level, you get the lipid and the detergent belt. And then they went on in 2016 to collect more data and have it at about 4 angstroms. And now there's a model with all 45 subunits and the sequence built into them all. And another group, Leo Sassanov, who had been doing X-ray crystallography on thermophilic bacteria, he also then switched about 2 or 3 years ago, and he's in Vienna now and has done a similar structure of the ovine rather than the bovine, and they both agree really quite well. So going back one, in 1996, it was Niko Grigoriev who wrote one of the softwares, FreeAlign, and applied it to this complex one. And he got it negatively stained and to about 22 angstroms by cryo. And so you then jump from 22 angstroms to 4 angstroms in something like 15 years. So that's a good example. So I'm going to finish now by kind of looking forward. So all of these structures, it works. Many people are happy with the methods. It's a growth area. But one of the things that we worry about is shown in this slide. So here are 4 different data sets for 4 different structures. And because these new detectors are essentially movie cameras, they record a sequence of frames, and you can either just add them together, which is what happened on film, or you can add them together and calculate the structure, and then go back later and ask which part of the exposure gave the data that contributed most to our structure. And it turns out that the very first frame, where the structure should be completely undamaged, is really bad. So it starts here. And there's different ways of... This is a B factor per frame, and this one was information content at 7 angstrom resolution, but it's the same idea. The first few frames, up to about 4 or 5 electrons per square angstrom dose, are really bad. Then you get a little plateau where it's good, and then it decays, presumably due to radiation damage. So we've been worrying about this because obviously the key to making progress and making it perfect is to figure out how to make this perfect. And so I'm just going to show you something that we haven't published yet, but Chris Russo, who's a young group leader at LMB, and we thought we should show this, even though the actual numbers haven't been worked out. So the red dots are how a really perfect image on one of these new detectors ought to be. The first frame should be really good, should have a 0 B factor compared to the natural structure. And then as you dose it with 1, 2, 3, up to, say, 20 or 30 electrons per square angstrom, roughly speaking, we don't have an accurate number for that yet, but roughly speaking, for every 1 electron per square angstrom, the B factor ought to go up for these frames by about 6 square angstroms. So that's the slope of that line. That's what we're aiming for. And when we reach that, we think that this is cryo-EM heaven that we'll be in. But in reality, there are various factors that kill you. So the first little gap here is you put the beam on the thin film of your proteins in ice, and there is radiation damage to the water molecules in the ice. They move around and causes the ice to move by about 1 angstrom for every electron per square angstrom. So after 25, the ice molecules have moved by 5 angstroms, and they've pushed all the proteins around, and particularly the small ones get pushed around more. So you lose something there, and there's nothing much you can do about that. The second bit, the blue part, we think that's a problem with the fact that the specimen is not a conductor. So you get microscopic electrostatic charging, which in the EM field we call the bee swarm effect. You defocus a lot, it looks like it's twinkling. And that is, we think, a defocus-dependent loss of contrast at high resolution. And again, you might be able to get over that in some way. But the biggest one is this pink area, which is physical beam-induced motion due to radiation damage. And for that, you have to sort of stop the specimen moving and so on. And then finally, there's a fourth one. The specimen does get all charged up as soon as you put the beam on it. And we call this an effect that John Berryman first noticed, that the patch you're illuminating gets positively charged. So the goal for the future then is to figure out how to make all of these things minimized or go away so that you can then improve the quality of the data that we have currently and make it perfect. And obviously figuring out the size of these tells you how much effort you should be putting into each of them. Okay, and then, so my last slide is just to go back and say, these are the experimental data, 3 different experimental data sets showing this information contact. This is the model that we have for it that's going to hopefully guide the future work. And then I'd like to finish by saying we're obviously delighted with how well the cryo-EM is working. It's going to be much better. And I'd just like to finish by thanking the various people that I've worked with over the years in the different... So my entry to electron microscopy came from hearing a talk Nigel Unwin gave in 1973. And then this group, Tom Seska, Joyce Baldwin, and so on, we all worked on these electron crystallography in the days before we switched to doing single particle EM. And then Nico and Bettina Bocciacci were the first ones to actually switch to doing that in practice. But other people, particularly recently, Vinoth Kumar, who is a young postdoc about to go back to India and set up cryo-EM in Bangalore. And then in the background, we're still doing this, a lot of detector development. So I hope that's given you an idea of a different person's trajectory than the other 2 speakers. Thank you very much.
Move to the last of our talks, which is from Marin van Heel. And let me tell you a little of his background. He was trained as a physicist, 3 physicists, I mind you, at the Technical University of Delft and the University of Groningen. He continued at Groningen for his PhD in biochemistry and biophysics in the group of Ernie van Bruggen, who brought forth some of these nice hemocyanin images that I first saw. At some point, he visited Albany. I'm not quite sure of the timing of all of that and how long, but we've heard a little bit from Joachim about that. And there they together worked out some of the multivariate statistical analysis procedures that are really the underpinning of what is being used for single particle reconstructions of the kind that we celebrate here today. He continued this work back in the Netherlands and then moved in 1997 to Imperial College, where he set up a group, and then in 2011 he moved back to Holland, to Leiden University. He is now associated with the National Nanotechnology Laboratory in Campinas in Brazil, and Marin's previous awards include the Ernst Ruska Award, which is named for the inventor of the microscope. Thank you.
Thank you very much for the nice introduction. It's a great honor to be here. I'm very indebted to the Wiley Foundation. I remember Wiley books that I had as a student, and I would keep them under my pillow when I had the exam the next day. And I really, it's a bit of a shock to me that today, nowadays, for the last 10 years, I probably haven't gotten into the library a single time, because most books, well, I either already have them, or you can look up stuff on the web. So the whole concept of books. Anyway, cutting a long story short. I'll start off with some acknowledgements, because I tend to get overly excited during my talks. And if I get too excited, I'm not sure that I'm going to finish, so I'm going to start with the last slide. So getting a prize like this makes you reflect a little bit on life and on things. And suddenly I was thinking about, there was this guy, Hendrik Casimir, who was a family friend, and my parents sent me to talk to him when I was 15 or 16 years old to see whether I would be a good physics student. I wanted to study physics. He was a professor in theoretical physics and the director of Philips' Eindhoven lab. I spoke 20 minutes to him. I haven't thought of him for many, many years, and now suddenly I start to look it up in Google, thanks to this award that I won. And then I go on to Professor Franken. Professor Franken, so just crucial 15 minutes of fame there. I spoke then later to Professor Franken. He was my professor of electron optics at the University Physics Department in Groningen. And Eddie Verweda, the other professor, he was a theoretical physicist, an instrumentalist, and a theoretical physicist. And those two shaped my development. And here comes the microphone because I'm too softly spoken, sorry. And then I moved on after that to do my PhD in the biochemistry department, and my PhD supervisors were a theoretical physicist and a biochemist. And so this was in the early 1980s, and then Marina Stöffler from the Max Planck Institute Molekulare Genetik in Berlin was instrumental in trying to get me to Berlin because I done some ribosome image analysis for her, and Elmar Seidler of the Fritz Haber Institute hosted me for more than 15 years, where much of the work was done after my PhD. It started off with my PhD here. So then later, I moved as a professor to the Imperial College. This was Wayne just said that. That was in 1996, if I remember, no, 1995. And in 2011, I joined a team doing electron microscopy at Leiden University, but remained an emeritus professor. I'm now an emeritus professor at these both universities. So these are the large scale. Here are mainly PhD students and postdocs. The list is not complete, whom I've worked with over the years, and very many had fantastic times and nice results. Many of them are now full professors, or the most successful is probably Lisa Borland, who did. She went into finances, and all the excellent mathematical skills that she now uses to become a multimillionaire in San Francisco. Many others remained in science, and that includes Holger Stark, who did ribosome work in my lab originally in Berlin, then later in London, and he's now a Max Planck director in Göttingen. Bruno Klauholz came as a postdoc to Imperial College, and now is heading structural biology in France. Tim Grant, Ardan Patvardan was a postdoc, came on a fish grant of all places. He is now the head of the database, the structured database where he deposits. The science that I'm talking about, Michael and Ralph, where are they? Michael and Ralph here have done software development and maintain our software on a professional scale over more than 25 years now. This is the group of people that I think of immediately in terms of the slides that I'm showing you today, and as far as they contain science, because it's not all science. Then Joachim already said that, and Richard said, so let me just talk about Joachim. Here is a picture of Joachim that I took. I was here for 6 weeks in this is New York, as you can see, visiting the Guggenheim Museum and having just a little trip here down from Albany, New York. This was for 6 weeks that I came here, and then 6 weeks in 1980 as well. And we did a very productive multivariate statistics collaboration. I'll get back to that later. And then there's this guy here. I didn't have my archive of negatives with me, but I didn't find a picture of him, so I had to steal somebody else's picture. As Richard maybe already mentioned, he spent a lot of time doing crystallography at the Fritz Haber Institute in the 1980s, because there were the fantastic cryo-microscope and these esoteric things that people were doing there on the Suleika and Sophie and fantastic microscopes. And we would spend evenings in the pub eating pizza and drinking beer and talking about the future of cryo-EM. So these two people, my co-prize winners here, and then I'll get back to that later, but here my kids, who I'm very grateful to. Two of them are in the audience, the two boys here. These, by the way, are the biochemists, and these are the musicians. And he now just decided to do something else with. So they can pronounce the names of the amino acids much better than I can, and they ran gels, and they're specialists in all these things. So just at least getting over these acknowledgements. There's some more coming at the end, to be fair. But I want to talk about not all the accomplishments, but about the problems of single particle cryo-EM. And I want to talk about sloppy statistics. We can't just be positive about our work. So here is a very important correlation curve. Correlations are very fundamental in electron microscopy. And here we see a correlation between the US spending on science, space, and technology, and how well it correlates with a correlation factor of 0.992 with the number of suicides by hanging, strangulation, and suffocation. This is not a political, this is here 2009, so this is before Obama and before Trump, so this is not a political statement, it's just about statistics and how you can misuse statistics and miscount things. This is sloppy statistics. There are other examples of sloppy statistics here. And you can count left and right, and somehow by some metric, the consequence of this sloppy statistics is actually quite serious. Here you have the NIH budget going down by 18%, at least predicted over the next year. So, not funny. Let me go back to a little bit of history now. This is serious science again, and I'll just scan through a couple of very important people. Here's Ernst Ruska. I went to the Fritz Haber Institute in the early 80s, and he would still come, and I took this picture of him. He was the person who built the first electron microscope that had a resolution better than the light microscope here in 1931. This picture was during the war. Then here we have Fritz Cerniker. He is a Dutchman who died just before I went to the university, as I never met him, to that same university where he got the Nobel Prize for doing the phase contrast microscope. And he did a very clever thing. He realized that an imaging machine is a double Fourier transform machine, 1 and 2, and you can manipulate the diffraction pattern, or actually the phases of the zero-order beam with respect to the other ones, and so you can visualize fully transparent objects very well. And this guy here is Otto Scherzer. I took this picture of him in 1978, if I remember correctly, at a meeting in Toronto, and he realized that the phase contrast microscope is, the electron microscope is also a phase contrast microscope, and it follows a transfer function that has this kind of shape. And you see these oscillations of the transfer function, and now think about it this is in Fourier space, I don't want to bother you, but the consequence of this is that if you have an object like that, this could be 3 angstrom information, and that 30 angstrom information, the microscope will show it with these oscillations. So what was black here turns into white, turns into black, and so on. You get all these contrast reversals. And electron microscopy is material is very radiation sensitive. You cannot afford to focus your sample, so you need to take pictures blindly and work this stuff out afterwards. So this is the theoretical aspect of electron microscopy. Then there's the practical aspect of embedding biological specimens. And here we have everybody, the 2 other speakers have already spoken about Jacques Dubochet, and he loves specimen embedded in water, especially in vitreous water. And this is the machine that we had following his research in the Fritz Haber Institute in Berlin at around 1985, where you plunge very rapidly, freeze your sample, and then get a liquefied, a vitrified liquid that you can image in the electron microscope, which gives you these fantastic images here of the 50S ribosome. Here one, there's another one there. This machine has, unfortunately, this was a pioneering machine. It has been dismantled and taken over by Richard Henderson, and he says that they're using the parts. They have almost recycled all the parts. And so this was a unique machine, and it continues to be working in some form. Okay, so this is a little bit of the history, and let me then go to cryo-EM today. We've gone through a big revolution. We have new microscopes, and we have new camera developments. The new microscope here is You can see here the electron microscope. Compare that to the early electron microscope that I showed you. As you can see, you don't see anything because everything is in a box, and all the equipment is hidden. And we see Sasha De Carlo here operating the machine from a distance. The distance is here just a few yards, but it could be a few hundred yards as well. And big development also is the new cameras. You've seen this. This is now the third time that you see this slide. And film was fantastic. And film was great. You had one sheet of film that will give you like 12,000 by 20,000 pixels, a huge amount of information. And other cameras in those days, like 20, 30 years ago, you couldn't do anything with it. But now slowly these cameras become at the same level as film. And of course they have the big advantage that it's all digital and the computer does it all for you. And you can take 20 images which you can't think about of doing film. So data sets are collected automatically through nice programs like the EPU from FEI here. And so the only problem now is that you get huge amounts of data, and up to a terabyte, and actually much more. And you can, having big data sets also means you have good statistics, and you can do fantastic things with microscopes now that you couldn't even dream of 20, 30, 40 years ago. So one of the things here brings me back to the Fritz Haber Institute in Berlin, and that is movie analysis procedures. When you take an image, when you look at at the image on the green screen, microscopes don't have green screens anymore. So if you look at one at the screen, suppose you see an old microscope around and not, you actually see the data coming in, and the data comes in like this. And this is actually a virus structure that we solved to 3 angstroms or 3.5 angstroms resolution. But you can see here that the actual data collection, where is my mouse? There. Well, it doesn't repeat. Repeat. Go. No. Okay. It's a one-off. But so you actually see the information raining in, and you see these virus structures here. You can hardly, when you see a single frame, you cannot. This is 300 angstroms in diameter. That the whole thing moves around and dances around, and this was something that was observed already in the early days. And here we have work from Wolfgang Kunert, Klaus Weiss, Hilde Kongel, Martin Kessel, and Elmar Zeitler, where working on a TV camera, they detected the arrival of individual electrons here. And the only problem was, you see here, the whole field of view was like 250 by 250 pixels. And no competition for 12,000 by 20,000 pixels that you have in film. So this was a technique way ahead of its time, and it took a long time for it to catch up. The whole procedures are almost a copy of what you would see today. And here we have a picture of Wolfgang and myself. Actually, I wasn't always white. And we were discussing some things. And I'm showing that because it was very fundamental work. He died, unfortunately, very young at the age of 59 in 1990, just after the wall came down. And but this work is now followed up by things like this here, motion correction now. And we see one of the important papers, 2012, if I remember correctly, yes, by Alex Briot, Nico Gregoriev, Richard Henderson, Bridget Carragher. They're all here. Clint Potter, I haven't seen him around, but he may be here too, and Steve Harrison. So this is in modern times, and what you can do then by following these movements of the molecules is that the power spectra that are distorted in the direction of the drift and distorted in the direction of the drift here, if you collect, in this case, it was 7 frames, then you can restore that information so you really get much more data, much more information out of your data. So this is the pre-processing that you have, and then you collect the data, and then you do single particle processing. Now this is a generic picture from one of the first ribosome structures that was reliable here in the 1995, 22 years ago. And so this is can be seen as as a classical 3D structure analysis where you have particles here and you classify them and you find angles between these classes, and from that you get 3D structure. You can calculate a 3D structure which you can project out again and refine the alignments. So this is a standard procedure. And in the beginning, one of the problems was we had techniques already to classify, but then how do you get these things to fit into one 3D? And that was a technique that was proposed here 30 years ago, exactly almost, and it took a little while to actually get it running. But once it did, it really became a very, very powerful technique. You don't need to tilt, you don't need a starting model, it's all in the data. And here we have a very early 3D reconstruction of the E. coli ribosome with the elongation factor TU bound to it, blocked there by chiromycin. And interesting here, this is 1997. The resolution is around 18 angstrom, if I remember correctly. And Holger Stark is the first author, and I was his PhD supervisor. And then the next slide here, you see it's still Holger Stark. The resolution went from 19 to 2.7, 2.6 in here. What year we're talking about? I think it's 2015. Exactly the same complex, a very stable ribosome. It just shows you how the development happened in those 20 years, 18 years. So this is one thing, new cameras, fantastic, higher resolution, more efficient data collection. And the other thing that happened, this is then Bruno Klaholz, is that we started to look at heterogeneous structures. This structure this is a release factor 3 bound to the E. coli ribosome, and it refused to refine better than, I don't know what, 30 angstroms or something like that, until Bruno Klaholz, who was a postdoc in my group at the time, said, well, maybe we should split it up into two 3Ds and refine them separately, automatically, and we did that. And lo and behold, you have a ribosome in a pre-translocational state and a post-translocational. You have the retching of the 30S with respect to the 50S, as Joachim was just showing. And this triggered. You have two 3D structures in the same soup. So you actually have time as well. So this is this is a very fundamental development towards 4D structures. And this then triggered a whole reorganization of our software, maybe by Michael and Rolf Schmidt in Berlin, and where you don't process with a single 3D, you process with many 3Ds all at the same time and refine towards a set of consistent different functional states of the structural states of the ribosome. So is there some water here? Thank you. So let me just go back to this generic story. One thing that I didn't say yet, Joachim has spoken about this issue of classification. You have many, many images, and then you average them together by multivariate statistical classification. And so what is the idea behind this? Biology is a mess, and you need a powerful multivariate statistical analysis tool to make sense of it all. And you need to find, of a complex system, you need to find the principal components of a data set. So this is a recent review here, freely downloadable. But at the beginning of this was here, the visit to Joachim Frank in 79 and 80. Took a while to get it published. And very late night sessions with Jean-Pierre Breteaudière, who was using this for medical reasons. And he hinted it in the direction of what we wanted to go. And these eigenvector data compressions make that your big data set becomes a more manageable data set. And in this more manageable data set, you can do unsupervised classification. You can just compare everything to everything and then average these groups and have nice 3D structures. Once you have these, having nice 2D images. Having these nice 2D images, however, nice 2D images doesn't bring you to this level yet. And there's still something here missing, and that is the angular assignment. And that came then in 87, and slowly and surely the pieces came together. Now, this automatic classification, this unsupervised, is a very important issue. And there are two types of classification. One is supervised classification, and one is unsupervised classification. The people, in terms of a single particle cryo-EM, the supervised classification is looking for one specific thing. You're looking for a specific reference. And you need to align with respect to a specific reference. In unsupervised classification, you compare everything to everything and then find those things. Now let us just first do this supervised classification. Supervised classification here, where you look for specific things and then process from there using explicit references. Now we have here one of the fundamental problems in single particle cryo-EM, and that is if you have an explicit reference and you want to find something, then there is a problem of the Einstein and noise problem. This was handled in Michael Schatz's PhD thesis in more than almost 30 years ago. And so what is the problem? If you have a reference and you align 5,000 images of random noise with respect to a reference, you put these random noise images in a position where they best match that. And by the time you average then these 5,000 aligned noise images and you sum them, lo and behold, Einstein comes out. Now, this is a very fundamental problem that you can, if you want, look for specific things and then find them. And there is a classical case here of a paper by Mao and Sodrowski and co-workers where they were looking at an HIV trimer outer membrane protein. And this paper triggered a reaction by Richard Henderson and by Sriram Subramaniam and by myself. And because this was really, in our eyes, a problem of reference bias. And here, in our response, in my response specifically here, I used a couple of reference images and random noise and picked these particles in random noise, did them unsupervised classification on these things, and here you see all these different views coming out again, including those of Einstein's. So unsupervised classification has a problem associated with this reference bias. Supervised classification. Unsupervised classification compares everything to everything, and you try to then do it as good as possible, yes, without biasing the data set. Now, there's different issues also with whole classification, because nowadays there are these black box programs, and you want to do a 2D classification or a 3D classification. And what is meant here is a mixture of things. You do alignments and multivariate sets of classification at the same time. So you actually have this and this mixed together. But nevertheless, these things are not clear. And the same thing here for 3D. That's a real issue that we still have in our field, and one needs to really be very careful about these things. A further fundamental problem, an a priori frustration. If you have even if you have the best of classification programs, yes, you would want the program to solve the problem for you. Now, it's like taking a picture of you and the audience and present those images to the computer and ask the computer who voted Republican in this audience. That is information that is outside the scope of the analysis. Yes, you haven't measured that. You can only look at things that have been measured and compare them to each other. The biological conclusion is something external to the problem, and you need to get that from somewhere else. So that's actually a pretty important aspect of classification. You don't expect everything from a classification program. It only looks at the data and sorts them according to certain criteria. And you can change the criteria. Here you have exactly the same data set. You change the criteria a bit, and you get a different classification. This is called nowadays a manifold. You're looking for a consistent story. That is another fundamental issue in these classifications. It's nothing to do with supervised and unsupervised. It's just fundamentally, it's outside of the scope of your computational experiment. So I showed you that you can have reference bias. There's also a way of avoiding that altogether. And by unsupervised classification and by alignment by classification. We don't use alignments anymore. And at least not in that order, not doing alignments with respect to specific references. So here we found a blood donor, and here we look at its blood. It's one our favorite test samples, Lumbricus terrestris, hemoglobin, in the cryo-EM. And then we do things like that. We just calculate the eigenimages of the data set, irrespective of what it is. We don't want to know, and then we classify all these different views, and you can get nice classes, and then you calculate it in 3D, and you refine, and so on. And then suddenly you can see this is the 112 subunit. This is a D6 point group symmetry structure. There are 144 heme groups. Here's the distal histidine pointing at the heme group here. And I have a movie for you from Afanasyev's PhD thesis. And here you see the 112 subunit, and it will show us in all kinds of directions and rotations. And well, that's the one. A triple helix here that Wayne Henderson knows very well. So the resolution on this structure is, this is, I think, also a movie. Let's see if it rotates. Here you can see the side chain is one of these helices. It's the most stable part of the structure in the center of the D612 of the D6 structure. And here we have the Fourier shell correlation telling you that the resolution is certain ones are at 3.6 and others are 3.8. There's slightly different groups of images in here. Now, one final little thingy, and that is here. The Fourier shell correlation is the metric that we use for looking at how good the resolution is. And that itself has become the issue of much discussion. I just picked up a recent paper that I had on my disk. I didn't even look at it. What you very often see now is there are two thresholds, 0.5 and 0.143. And people then say, typically quote the 0.143 structure because it has the highest resolution. But these lines here are based on statistics where the noise in one ring in the Fourier space is correlated with the signal in the other ring or vice versa. And we've seen this one already here. Here we were looking for the maximum in noise, correlating the two and finding then Einstein. What we're doing here is slightly different. We're just multiplying, we're just finding the correlation between random noise and Einstein. And that is 0 on average. But it's not 0 if you actually measure it because there are statistical fluctuations. It's very different and people assume this to be 0. And that is not correct. And that's the basis of these straight lines that you see in the resolution criteria. This here, being 0, means that these two factors, the signal and the noise, are orthogonal. And if it's done correctly, then it's square root n, where n is the number of measurements that you do. Now, let me tell you the difference between independent and orthogonal. Oh, sorry. This is the last one. Between orthogonal and independent. See here, you have a couple that are wildly in love. And they have just entered this apartment. And if you see one in the kitchen, the other one will be in the kitchen. The density distribution of these two individuals over, if you calculate the inner product over this, it will be 1. However, after 7 years, then person X may be in the kitchen, and person Y may be or may not be because it's completely independent. So you have a square root n. There's so many rooms, and the chance that one is here, and so this is statistically independent. Now, after 7 more years, if person 1 is in the kitchen, person Y will not be in the kitchen. And if person X is in the living room, person Y will not be, and vice versa. Now, that is the inner product of these density distributions is 0. So that's what is called orthogonal. Now, that is a little bit of So fixed threshold values are wrong. Let me be controversial, but everybody uses them. So who cares? Well, there are all kinds of reasons not to do this. All kinds of sloppy statistics reasons. And also, you get an idea that these things are not valid. Actually, it's better in terms of a metric resolution than your standard R factor in X-ray crystallography. And you never know, suddenly these things have weird consequences if you don't watch. Okay, so actually, it's very, very, the cryo-EM stuff is so nice. This area is very important. The higher this is, the better. Here is an ongoing result. This is all technology, but now we're actually looking at the biology, and we see here Eduardo Jorjale was very enthusiastic when I spoke to him a few weeks ago, looking at a cavity within the 112 subunit where he sees 3 glycosylation sites, and this is ongoing work. I will not. There are all kinds. Okay, we'll not go into this. And then finally, there's one more thing that a person that I want to acknowledge, or a few persons, 3 people that I want to acknowledge. First is my parents. And here, this is an unfortunate history here. After my father came back from camp, my parents married a few. This is in July 1945. And moving away from the misery of a broken Europe, they went on a boat crossing the equator to Brazil, and here was this lucky guy on board, and so it happened that I was educated in the interior of São Paulo, and in those days maybe you needed modern super constellations to fly there from the first world. Today, our world is completely dominated by Brazilian airplanes, and high technology from Brazil. Here is one of the new synchrotron that's being built. It should be in operation soon. And here, cryo-EM is being installed to complement the properties of the new synchrotron. And so maybe I'll be signing a contract there soon. We also have a school, which we're going to operate for the 8th time already. And with that, I thank my wife and you for listening to me. Thank you very much.
Thank you, Marin. And if Richard and Joachim could come up to answer questions if people have them. So I'd like to begin by asking Richard a question about these numbers of particles that you need to get to some level of analysis, which I think are based on the situation where you have a single unit. Have you looked at the question of how that's affected when you have distributions that might be, multiple discrete states or maybe continuous ones like Joachim has said?
No, we haven't, but...
I think you should.
No, we haven't, but many of the computer program systems now, as Marin had mentioned, for example, do these multiple states. You can choose 2 or 10 or 100, and I think, roughly speaking, if you're going to try to resolve 100 different states, you're going to need these numbers for each of the states. So you should just multiply by the number of states.
So I wonder if you have an idea as to the use of contrast agents. So years ago, I remember Richard's work was using gold glucose and things like that for your crystals. Do you think that negative stain and things like that are no longer useful, or should we just put our sample on a cryo grid and go to town with the detectors? Anybody have an answer? Or?
Do you still do negative stain at all?
Well, I think it's really, if you're dealing with a completely new specimen, it's a good idea to get started as a very basic screening, and you might get through over this point very, very fast, like in a single afternoon. But I think it's always a very good first step, especially because the time on microscope has become so expensive.
I can say, really, the great thing about this thin film plunge freeze method, you can go from pH 1 to pH 10, and you probably have to have gold grids rather than copper. You can change the salt level from 0 to 1 molar or something like that. So you already have a big range of conditions that you can try. Nobody's really working on that, but one thought was perhaps if you embedded your protein complexes or molecules, ribosomes, so on and so on, in a different medium, perhaps you'd be able to take pictures for longer radiation damage. And Ken Downing and I once spent several days embedding our specimens in 10 molar lithium fluoride. And, when you put the beam on water, hydrogen gas, oxygen gas comes off. I don't think you'll be surprised to know that when you do the same thing with lithium fluoride, 10 molar, you get fluorine gas and lithium metal, and it doesn't help you. The dose is exactly the same. So I think we're very keen on embedding it in water or aqueous media.
If I may say something, my impression always was negative stain. The problem is not so much the negative stain, but it's the dry negative stain, the taking out of the bound water that deforms the molecules. I think we haven't seen the limits of cryonegative stain still.
I have a question.
Just one quick question while we have such a distinguished panel. Where do you see this going? We've just seen the resolution revolution in the last few years. What's next?
Cryo-EM heaven is next. and then, it will reach a sort of limit at some point. I think that's still a certain factor away. So you'll need less images, higher resolution, more multiple states, and it really will become, well, it's already pretty good actually, but it'll become more powerful. But there is a limit, but we're not there yet.
Yeah, I already mentioned time-resolved cryo-EM. I think this is a very exciting development because in the normal EM preparation, it always takes a few seconds, and any short-lived states are already gone. So we have currently something in place which has time intervals between 10 millisecond and 1,000 millisecond. So we cover short-lived states that cannot now be seen with a routine EM. And we already see states that have never been visualized before.
Another question here?
I think you were just getting to this a second ago, but I was just going to ask if you wanted to briefly go into anything you're excited about the new spray plunging that just came out. But I think that's sort of along the lines of the time resolved.
I'm not sure we caught.
I didn't quite catch it. Yeah.
Sorry, I was just going to ask if you wanted to go into a little bit about the new spray plunging technique that just came out. The time resolved would be like the nanospray on the
spray technique.
Yeah.
Oh, the spray technique. We developed the microsprayer independently from time resolved, and eventually it's going to be all in one unit. But we found out that the sprayer itself is a viable alternative to the blotting technique, and it is better controllable than the blotting technique because one can sort of vary the gas pressure. And the other thing is also if you deal with some kind of component that will not be stable over even a few seconds, then the microsprayer has an advantage because you really get the specimen onto the grid almost instantaneously. So you might want to look at the structure paper that just came out a week ago on the microsprayer, Feng et al.
So with high resolution, we are able to see water molecules and ions also. But then the question is, how do you actually differentiate between different ions, zinc, magnesium, from this structure or from this density? How do you want to what criteria you want to look into it, and then how do you exactly differentiate these different ions?
Yeah, so I think the question is, if you have a map and it's fine with the polypeptide chain or the nucleic acid, the backbone, phosphate, sugar, and so on, but what about ions, where you get a single dot there? And, you know, in X-ray crystallography, they have a lot of trouble differentiating between a water molecule, a sodium ion, and a calcium ion. And, you know, they have the same number of electrons, but the geometry is the geometry, or sorry, not calcium, magnesium ions. They have the same number of electrons, but they often do it by the different geometry that you expect. So I assume it'll be the same with EM, and there isn't yet really a very good theory about the amount of the form factors for the atoms or the ions or whatever in electron microscopy. There are theories that are idealistic, and then there are other people beginning to think about it, but there isn't really an established agreed level that you should be looking for. There's some people who think, you know, positive and negatively charged ions will show up differently. They must to some extent. And then, of course, there's this other thing, that the scattering factor isn't linear with the atomic number, but it sort of plateaus over. So uranium ions wouldn't be as strong as they are in X-ray crystallography, but they'd be much less strong, maybe because it's Z to the 3/4, but there are also variations depending on the bonding. So that's a very good question, but it's a sort of unresolved area. And I did have an email yesterday evening from Rod McKinnon asking exactly that question. So, but I didn't have an answer then either.
Well, the answer is do crystallography, because
yes, of course, yes.
Because you're not limited, as you were suggesting, because in crystallography we can use anomalous scattering to distinguish things very well. Even magnesium and sodium, for example, we are able to do refinements of the scattering factors, the anomalous scattering factors. We have to take data at lower X-ray energies. But it is, and we've thought about this for EM problems as well, and it's a vexing problem. We don't have a good solution on that kind of thing. For example, in crystallography, going to the anomalous scattering as well, we very commonly use selenomethionine as a substitute for methionine, even to introduce selenium sites so that we can get benchmarks of where we are. And we don't have very much to do that we can do with on the EM that front. There may be some things in the future.
Perhaps I could ask us a question. So has anybody yet done any cryo-EM on, for example, selenomethionine-labeled proteins or complexes, say the ribosome that was grown up in a complete selenomethionine area, so that that would be quite an interesting thing to compare between an X-ray structure and a cryo-EM structure. That would tell you something about atomic scattering factors for electrons.
Mm-hmm. I think that would be nice, actually. It could be done easily enough, I think. Okay, now I really don't see any hands. And it remains then to thank our award winners, to congratulate our award winners, and to thank all of you for being here and paying attention. Thank you very much.